Hello, welcome to the stream. I'm Jun Chan, and today we're back on our streaming tools in exercise, our project. So let me do a little bit of housekeeping here. And we are April 24th, and we are working on streaming. So last time I wrote a couple of to-dos, and basically the idea is, what would a declarative API for GStreamer look like? And since it seems that the graph or the pipeline network or pipeline graphs are going to be critical to the underlying data structure that we will be modifying or using as the underlying state for the declarative version of our pipeline, in the way that a component tree is the underlying state structure for a declarative UI framework like React or the GTK declarative library that Oscar Wickstrom did, and that we are using a little bit as a jumping point. So equivalently to that tree of component, or that therefore that kind of underlying data structure, that's the tree mapped to a tree of component containing each other in a UI settings. Here we're kind of talking about an underlying graph of sorts. I don't know if there's maybe a smaller data structure that would work for that, but the idea being that we can then describe the actions that we do on this graph, both construction and mutation. And then I also envision the idea that maybe nodes in this graph actually can hold their own state. And for instance, nodes could hold a tree data structure in case, for instance, some of the nodes had, let's say, component data structure, like more traditional UI components to them. So one example could be that, in a pipeline which had 4 components, you could attach a UI to the components and the parameters that can be modified on them, like the type of encoder, the bit rate of a particular input, or different settings that GST pipelines, GStreamer pipelines have for their GST elements. So we could maybe use the introspection to actually generate those local tree style UI components, and they would together fit into more of a network or graph. So I've been playing around a little bit with graphs in Haskell as a consequence of that, and some of the data structures that I thought maybe would be nice to explore next would be things like arrows or free arrows, which are used to create a component graph for FRP, for instance. Arrows are free arrows, something I'm interested in playing with. And then there's something even maybe more ambitious, which is this parametric higher order abstract syntax-based structured graph representation. And then knowing that whatever the version that we do, we need some kind of polymorphism, or because each element of each vertex and each edge of the graph might have different types. So arrows might actually fit the bill quite well. Structured graph, I'm not even sure. So so that's one possibility. The other possibilities is to explore something a little bit different, which is how to actually bind to the GES layer of GStreamer, and do things like instantiate a GES pipeline in Haskell and a GS timeline. So I'm a little bit unsure of where I'm going to go at this particular point. So I'll actually just take a little break, and I'll be back, and we'll pick a direction. Okay, and I'm back. So yeah, I gave it a little bit of a thought, and what I think is that, well, I do want to go the direction of arrows and free arrows. That's going to be essential. Plus, I really super interested in the theoretical aspects of this and trying to use that for implementation too. However, I feel that so far we've been doing a little bit, we've been a little bit heavy on that kind of more theoretical side. And so I don't want to leave completely the GES pipeline thing hanging. So I want to do a few things. So maybe like try the GES launch and see how that works, and then at least map out what would be the steps to instantiate the GES pipeline in Haskell, and whether that means generating bindings for GES or not. So so let's do that, and maybe I'll put a clock on myself. Say like I'll do this for 25 minutes, like a little bit like Pomodoro style, and here we go. All right, so GES launch. Can I even use that? GES, right? No, I can't because I need to import this, I suppose. Let's see how that work. Oh no, power. Okay, I see. So right, the structured graph stuff is here. So I suppose we want to move it here, and well, GES install GStreamer, GES launch. Multimedia timeline, it's the GStreamer. Okay, so that's one of the 3 command line tools that appear. So what seems like top level things. So clearly we would just double check, but we should have GST launch. Yes, we do, but we don't have GES launch. So what could it be? What could it be? Installing on Windows, GStreamer editing services. Let's get to the top level entry for this. GS timeline, initialization. So you know what's probably happening is that it's dependent on a certain version of GStreamer. So far, how we've been doing this? We've been doing this through flakes, and we've picked up GST from Nix packages unstable. And we have GST or GST dev tool. So let's maybe let's REPL into this, or at least REPL into, let's say, Nix packages. I suppose. So in theory, we used in one of our other projects a way to make the REPL connect to the flake. Well, you know what? Let's look at how we did that, because that's not that's quite interesting. I think we did this with the nbody work, and yes, apps REPL beam. And so let's see, can I just in here add apps REPL, and then what's the way of actually starting this? It might be just yeah, I forget actually. Did I put this in the README? Yeah, no, I don't think so. and that's not my to-do. How do we run that? That would be something like nix. It wouldn't be nix develop. No nix REPL. Okay, so I suppose I need to do something like copying this and searching for it on the internet. Nix REPL. And then we do nix run ./REPL. That's the trick. And so let's put it in. Well, let's put it in the README for our streamline thing. So I launch REPL with flakes. Boom. And boom. Okay, and I think we can run this from inside the shell. For no reason. And then GST, or is that going to be in next packages? Okay, what's in there? Inputs, next packages. I think I need to import that, don't I? I need to say, oh, right. Right. So yeah, packages. I need to say packages equal. Otherwise, it's going to evaluate the world. And then here I can do GST all, and then GST editing services. Amazing. All right, so let's add this to our list, and let's maybe make our array a bit better looking here. I think in the next way it's going to be a little bit more like this. Packages, is that really needed? No, probably not. And GST all one.gst editing services, and I save, and I exit the REPL, I exit the develop shell, and I re-enter the develop shell. So I'm looking at this and I see that here I'm overriding the Cabal extra libs or whatever, yeah, extra lib libraries. But I should probably instead write that inside my Cabal file, otherwise it won't be portable, right? But okay, moment of truth, GES launch. Oh yes. Okay, so let's see what we can use GES launch with. And inspect action types. Okay, we can do that. Okay, like so. And nothing happens. Okay, why not? So we don't have action types. Welcome. Plus clip, path to media. Okay, let's try that. Sorry about that. And videos and sample. Hey, so that just works, and there's a position. Nice, and it just stops, and yeah, very cool. And maybe the finishing was not clean. Is that true? Let's see. Or is it that I closed it? Oh yeah, no, the finishing, it says done, but then there's a bunch of warnings. Probably not too much of a worry. And then what? Simply play the sample from its beginning to end. And this will say what? Assuming media is a 10-second, well, that's the case actually. This will play the sample for the 4th second to the 10th. So we just add in point. So it's hard to tell. Will it stop at 6? Yeah, it did stop at 6. Yeah, nice. In point 4. So that all seems to work properly, right? Okay, so we can check that box. We've played a little bit with GES launch. Now what? Now instantiating a GES pipeline in Haskell. So that's where things start becoming a little bit more hairy. So let's see how we could even approach this issue. First of all, we need to look at GIGST. And here we have these objects. But clearly we don't have anything that's editing here, right? We don't. And we do have a more recent version of the package, and that doesn't have editing in it, right? No, it doesn't. So all of these things like pipeline, right? That seems very locked to this particular framework, right? To GStreamer itself. So how does building these things work? Using the generated bindings. It should be rather easy to generate bindings to any library with GeoObject introspection support. See the example in the bindings folder. So no GES in there, but bindings. The Docker file, this one, build tools, I suppose, for the bindings directory can be generated by using cabal run gen build blah blah packages.sh. Okay, there's OSX and packages. Packages does what? Create binding cabal files package dependency for the given distribution. Okay. I see. So that's going to be tricky for us because that assumes Ubuntu or something. So I suppose we could run them in the Docker container. Or if you want to generate a single .cabal file by passing in directory where the binding is, for example, cabal run gen build GTK4. So there's a folder GTK4, there is a folder GTK4. And in there, what do we have? I see. So in there, we do have sort of a declarative way to pull in GTK its dependencies, which I suppose then will go and do the introspection directly from the binary or something. So let's take a look at whether there's forks or maybe even a pull request for GES. I mean, it's not completely impossible, right? Forks. And what do we have here? VIPs. Don't know what that is. VIPs bindings. Interesting. And what else do we have? Let's go callback type, signal, proxy, monoid. IBIS. GTK GTK sheet. Yeah, so definitely, okay, so let's switch generate binding for GS. I suppose it will be based in this, use this. Probably best to use an Ubuntu Docker container. And what's GST video? GStreamer video? I have no idea. Ah, it's just the GStreamer plugins. I mean, maybe we could adjust this approach to NixOS as well. It depends a bit, I suppose, how build tools work. Let's take a look. Gen build info. So gen build info, I suppose, is the thing that's going to introspect, and it takes the name of the library, but not just. I think the name of the library and the .info is going to basically what is this going to do? Going to look at the .distribution package. Yeah, so they do this in CI, so maybe it would make sense to look at the CI pass, see how that works out. So there's either list. So all of this, I think, is passed to, so this will do them all, and this will do only one of them. So, okay, when adding new binding, it might be necessary to augment the search pass use for .gr and .typelib file. It can be done by setting the environment Haskell gr search path and Haskell gr typelib search path respectively. Okay. So gen build info will take a folder, if I understand correctly. Let's look at main, get args, blah, gen info, takes a directory, and then from this directory does gen bindings in dir. And if there is one, and otherwise it will do something for each. Gen bindings in dir takes the file path, needs a pkg.info. Then we'll do something that feels like generating. Get the info first with this read gr info, gir info. Read gir info is here, and it just reads the file, and just parses it into either an error or just a straight file, really. And then it say generating whatever the name. Oh, okay, so this passes the JSON then. Oh yeah, A is ASON, I suppose. Yeah, so it passes the JSON, and so we can then pick the name for it, for instance, or the version, and that would display that. And then we take that info and pass it to exposed modules and dApps. And exposed modules and dApps is going to take the info and the dir and configure dry run with all these things. So it kind of makes me want to I do still have 6 minutes on the clock, so I think I will actually give that a shot in an adjacent folder. So where are we? streamline. So we'll make it there. Well, we know we will. Well, we have Haskell GI here, so we'll go into Haskell GI, and we'll go into bindings, and then we'll cabal run. We'll cabal build first. And then we're going to need to build whatever that is, right? Whatever the we don't need accelerate. We need to be here, and we need to go in Haskell GI bindings, and we need to do something that will be like well, I suppose it would be maybe a little bit like GST video, so I think so. Let's double check by seeing what's in there. Yeah, that's GStreamer plugins base, and depends on GStreamer audio. It's not obvious to me what that really is. And then GStreamer tag. Okay, if I look at when I did GES here, we don't have audio in there, or right? And this seems like they're in the plugins, so somehow this is a module from inside the plugins. Is that really what it is? I don't know. But I suppose the possibility is that this is actually all this package.info stuff is in the source repo for GS. So let's go check that out. And that's documentation. And so when in GS free desktop GitLab. There we go. And does this have, are we in the right place? We're in master, we're in start.js, so let's go to GST editing services here. And let's see whether we have something like pkg.info here. Bindings Python. All right. Let's go in GS then, and parse meson. Okay, so let's instead do GST editing services and pkg.info. So clearly this is specific here to this Haskell project, I think. And let's assume, okay, let's look a little bit at, let's compare. So these have pretty much very similar sets of dependency. This seems to be lower version, but all of the audio and video and even the tag thing seems to be depending on the same set of things, and that GST depends on a little bit less. So actually it seems like it doesn't pick up the transitive dependencies here. Okay, so let's take tag, duplicate it, and say GST editing services, and then say, well, those will be binding versions. So I suppose we'll need to say GIGES 101 GStreamer editing services library generated by Haskell GI. GStreamer editing services binding. Do you name I don't know, but maybe we'll do that and say GST-GES. Do we have overrides? Well, let's pretend we do. Here I'm a bit tempted to remove this, but we pretend that we're in Ubuntu and do libgstreamer plugin space and libgstreamer, and we do GES, or editing services. Hope that will, yeah, tool for user GST editing services, editing GES10 tools. Otherwise it's libGES10 dev. So I think that's probably what we want. libGES, yeah, that's that sounds plausible to me. So libGES10 dev. Then we depend on the same thing, and we say that it depends on pkg config depends on. All right. How is it here? GTK4. I see. I think this is probably where I need to actually use my flake for now, especially if I'm going to be trying to install this through Nix. I'm not sure, but I say GST editing service. It's what feels like maybe it should be. Something like that. Okay, and then let's see whether it compiled. It failed. I see. Really? We don't have pkg config in the shell. How peculiar. And yeah, there's no Docker. Oh, there is a project.nix though in Haskell GI. Oh, that's pretty cool. That's actually super cool. So how? Oh no! What? This is my stuff. What I? Oh, so this is me trying things inside Haskell GI. Holy moly! I don't even remember doing that. Okay, so yeah, this is my own stuff. So no pkg config. How can I just get it in by saying pkg config in the shell here? Actually, native build inputs. Let's go back to Streamline, and well, maybe that's actually my clock here, and I should just note what I'm doing next here. I think that makes sense. So best to use an Ubuntu Docker container. I don't know about that, but what did we do here? We need to have pkg config in the Linux develop shell. But what we did is we created a GS folder in Haskell GI bindings. And we need that to build the build tools, and more specifically gen build info, right? Okay, so that's next steps. Excellent. So now we go back into fairy tale world with arrows and free arrows. Oh yeah, so excited to give that a shot. Okay, first of all, I suppose, is that something we already have somewhere? No. Okay, so Haskell graph tools arrows is something I was looking at just a second ago, and this says something like using arrows to kind of model graphs, so maybe actually print out a graph. And then Gabriel Gonzalez says, well, use free arrows, you'll have the structure of the graph that you can display the diagram, but then you can also use it to interpret something else, which is exactly our setting here. We want, if we have a structure such that we can describe our pipeline through it, then we can use it also as a way to, that we can run an interpreter that will interpret the free arrow graph into an actual piece of UI. But then we can also run it, and we don't need to maintain two separate things, and that seems like perfect. So let's see which Stack Overflow issue he's pointing to. Useful operations on free arrows. You know, free monads are useful. A package like operation will make it easy to define new monads by only caring about the application-specific effects, not the monadic structure itself. You can easily define free arrows analogous to how free monads are defined. Okay, let me take notes right there in the form of maybe, well, I suppose we could do this in design. Yeah, design is not too cramped at this point. So what's wrong with those things? Yeah, sure. So let's do this, and then you would need array, and array would be import data array, I think. And then you need text, and that would be import data text, and then you seem like you would compile, so that's good. So now we're looking at this in the kind of free arrow world. So maybe here we say free arrows. Ooh, interesting spelling, and we play. So first of all, apparently GEDTs are very well. And then what? Free A and effects. Okay, so we import a bunch of stuff. Let's import the stuff. And okay, let's just import that stuff and then read it when it's here. So free A FAB is the GDT such that we either pass it a function and we, I suppose, can lift it into a free arrow, or we pass it an effect. So that sounds like a monad. So that's great that this free arrow structure allows to have effectful arrows. So we definitely want that. That I think feels a bit like the M in the what is it, monadic stream function kind of thing. Like let's write it. It's an MSF AB, MAB, S A is something that, what is it, takes an M, an S, returns an M of a B. So is it MSF MAB? return MSF MAB. It must look a little bit something like that, but MSF internal, I think it's where it's defined, GitHub. Validation function, internal core, and hello. A to M of B and MSF MAB. Holy moly. I got it the first time round. Pretty nice. Okay, so it makes me think of this where M is F, basically. So you know what? Let's start adopting it because sure, it is going to be an effect, but let's make things look a bit like how we used to. That may be useful to spot patterns and whatnot. Okay, that's not going to be useful to spot patterns. And M and M. So that's nice. And so, yeah, so MAB, so that lifts. What is this though? Does this require M to be of kind star to star to star? In which case M is actually not appropriate. So maybe I went a little bit fast here because F here has, given this type signature, F seems to have kind star to star to star. In which case I'm not sure what we're saying. This effect is this effect. Well, I suppose pure text a function, that's fine. Go from A to B. This is also going to have like the profunctor instances, by the way. Well, in fact, in PureScript, arrow is a superclass of profunctor and strong, if I remember correctly. And we'll want something else than A1, and like we'll do CD, and it's going to be just a tiny bit less readable, but that's life. So that's going to be A, C, and B and D, which is strength. This in both. So there's, yeah, that's sequential composition and that's parallel composition, and that already feels a lot like it feels very right for some reason in terms of what we'd want as primitives for composing diagrams or composing networks graphs. But we shall see whether that turns out to be correct in practice. My question is, what would be the most useful generic operations on free arrows? So analyze and visit. So that's a fold, I think, and then eval. Eval seems to transform the free arrow into an arrow. Yeah. Oh. I heard that this question may be too awesome for Stack Overflow. That's so funny. Okay. I worry that this question. May I ask what kind of application you're looking for? Short Visher, like super amazing person. I ended up using applicatives instead of arrows. I see. So Cactus can drop his thing, but then RID is just ID. Okay, well, do you have RID somewhere in there? Don't seem like you do. That's just in there. Another amazing. You mean I should set ID to ID in the category instance? Ah, right. Okay. ID equal pure ID. Oh, I meant for your definition of first and second. Okay. Oh, and 6P joins in. Holy moly, this is all the real heavyweight champions. And then, yeah, sure, then gives the definitive answer, but we will get there. Category instance is associative visits. You can distinguish ABC from ABC. Who? Wow, didn't realize that. Is that true? Hold on, you mean this particular category instance, right? Because category, I think, needs to be associative. That's the composition law. That A, B, parentheses, A composed with parentheses B composed with C is the same as A composed with B, parentheses composed with C. But then you're saying what? That this is actually not associative because of this definition of free arrow. Okay, maybe that's the case. I think there's actually a package now for free arrows, so we'll also check that out. And when was this asked? 2014. A free functor is left adjoint to a forgetful functor. For the adjunctions, you need to have the isomorphism, natural x and y of free yx, free y 2x, isomorphic to y to forget x. In what category should this be? The forgetful functor forgets the arrow instance. So it goes from the category of arrow instances to the category of all bifunctors. Right, so that's the thing, that f is a bifunctor, and free fab is a bifunctor. I suppose that a profunctor is a bifunctor, so it's a bifunctor which respects some category-like composition law, I would say, or at least pre-composition and post-composition. So it goes from the category of arrows instances to category of all bifunctor. So it forgets. What does it forget by going into the category of all bifunctor? Yeah, I don't know yet. And the free functor goes the other way. It turns any bifunctor into a free arrow instance. The Haskell type of arrows in the category of bifunctors is type of x2y, a twiddle, is 4ab, xab, yab. So this is, I think, an AND or a coAND, and you see these things in definition of profunctors, actually. It's the same for arrows in the category of arrow instances, but with addition of arrow constraints. Since the forgetful functor only forgets the constraint, we don't need to represent it in Haskell. This turns the above isomorphism into two functions: left adjunct free a to xy, and then right adjunct arrow y xy to free a xy. Okay, so free xy would be the free thing, and it can be the left adjunct transforms it into an arrow, and then the right adjunct takes such a thing where arrow y, for some reason, I think arrow xy, and then gets a free arrow from it. Left adjunct should also have an arrow y constraint. Also, no, it is arrow y. It turns out it is never needed in the implementation. It's actually a very simple implementation into the more useful unit. So unit x to free a x. So that's kind of the partially applied free a x. So or free axy, I believe. But this is mean free. I don't know how this associates actually. So unit is x to free ax. And unit is your effect, and right adjunct is your eval a. You have exactly the function needed for the adjunction. You need to show that left adjunct and right adjunct are isomorphic. The easier way to do that is to prove right adjunct unit ID. In your case, eval effects equal ID, which is straightforward. What about analyze? That's eval a specialized to constant arrow. That's a constant arrow. With the resulting monoid constraint specialized to the applicative monoid. There's a resulting monoid constraint? Oh, here. Right, hold on. Analyze. Okay, all right, I see. So eval a is the right adjunct that goes from the arrow to the free arrow, from the arrow. So I thought that was actually the free arrow to the arrow. No, I think it's the free arrow, some interpreter for from F to R, and then it goes into R. So that's the interpreter, I think. So eval a takes an interpreter and transforms a free arrow into an actual arrow. So a right adjunct that eval a, right adjunct is eval a. I'm seeing this in the other direction. But okay, so analyze is supposed to be what therefore the right. So fr is instead of r, a is b's. So yeah, specialized to this constant arrow. And where f is an applicative and r is a monoid. I see, okay. Huh. Right, so yeah, so that's a particular way to traverse a free arrow data structure into some kind of monoidal result, which is probably going to be, maybe that's going to be the shape of our, I wonder, like I'm thinking, is that going to be the shape of an underlying graph, or like one of the interpretations of it? So the fact that it's a monoid makes me think that that's pretty good, for instance, for it could be very good for a drawing, and then maybe the applicative effect would allow to do things like actually a tree structure, maybe, like for at least kind of like set composition or containing relationships for things in the 2D space, like layout algorithm of sorts in the F, maybe. So that we're not monadic because we don't need to know what's in the other branches. We just need to know how we position ourselves compared to them, maybe. And then maybe we build up yeah, well, the monoid is really the return value, so I suppose we can do whatever we want here. We could just be returning an R. I mean, this is arbitrary. It probably makes more sense to Well, does it though? Because here this is narrow, whereas here is a monoid. Yeah, I suppose like there's tons of eval-like functions which go from the free arrow to whatever type we want, like to an A of sorts. So like it's like FA to A. Well, except like this is kind of FA to B, so not exactly eval, but maybe more natural transformation-y. Okay. And to do constant arrow with the relative monoid constraint specialized to the applicative monoid. Analyze visit get type guess count value blah blah blah. With is that a smaller version of this? It might be. Yeah, in function of eval a. Whether here it's not defined in terms of eval a. Cool. Wow, amazing. Look at this 0.3 beauty there. New type const. Okay, so that's the constant arrow. I see. You defined a special type for FR. And app from the reducer package. App being right, the superclass of applicative, I think. Edit, I almost forgot. Free A should be a higher order functor. Edit 2, which on second thought can also be implemented with right adjunct and unit. HF map, ta-da! And we step into the higher order world. Okay, so now I'm quite confused, and that relates to the associativity of free A. So were we all the time, in fact, looking at free A x to y instead of free A of x to y? This is a little bit confusing. This is a whole lot confusing. There's another way to define free functors for which a prepackage on a package recently doesn't support kind start. It does now. The code can be adapted to free arrows. And here comes the sort of final version of things. If you don't need the introspection your free A offers, this free A is probably faster. And we get even fastness. So what is this? New type free A FAB. All the higher order things. There's examples. How nice. It's also updated. How very nice. Automaton. So we are for sure hovering always in the same corner of the world, because effectful automatons is like, this is a what, a melee machine, right? Like a effectful melee machine, which is an automaton. And okay, well, unfortunately there's no example for free arrows here, but let's look at how free is defined. So that's free, and you're not using free here, you're just deriving this. All right, the code can be adapted to free arrows. So I think that's definitely the final version, which doesn't use JVTs. And say that if you give me something that goes from F to R, I don't know how to read these declarations yet. I think it's that if you give me those two things, then I create a free A. I think that's right. So that seems like that's another way to define things. That's slightly more indirect than this version, right? It might be equivalent and isomorphic, but, and you can probably create something that has more of these this structure. So maybe we want to actually start from this, at least until we get a handle on it before we move to this. Okay, so I'm still gonna copy that and make a note. This below is probably faster, but harder for me to understand at this point. Okay. Great, but so now also I think there is also a free arrow package, right? So let's go check out what the Haskell free arrows is. Probably quite a lot more. So here we go, we have a free arrow here and a free category, and that's more like this, right? So it has an effect and has ID. Interesting. So okay, R is pure and prod is the yeah, so that looks quite a lot like yeah, strength, whereas this is maybe more than strength. I think it maybe strength and co-strength, or the fact that you can also compose your inputs. So definitely interesting here. So there's also this. Okay. There's also boom. Oh, check this out, and that's the CPS style. So actually, this is CPS style, which is why it's faster. Amazing. So yeah, you can tell it's exactly that, kind of same principle right there, with using this definition. Or I suppose I should also copy paste this definition there. This one. And free interface free algebra. So that's eval, I think. Yeah, a bunch of stuff to do here that work on the higher order version, which is kind of, I suppose, the H3 in short vicious package. Building free arrows from components. Ooh. 6P 2017. We are closing the gap, folks. How are we related to strong profunctors? Okay, check this. Let's check this out. Profunctors and arrows. Yeah, arrows are strong profunctors. We know that. Good. I thought I combined this and applied them to arrows built from profunctors. So Free arrows are arrows built from profunctors. We get to use arrow notation with those? I thought I'd have to give up arrow notation. That's amazing. Heteromorphism? What is this? I'm going to call an element of the type PAB where P is perfunctor, a heteromorphism. Okay, so all right, like because an endomorphism would be from an A to an A, so sure. Product that isn't much of a product. As I described a while back, you can compose perfunctors. Yeah, but yeah, indeed, that's where you need to do the end thing, and that perfunctor are more like relational than functional in some way. It's kind of intuition I built for that. Compose FGDC for compose FDA GAC. Right, so for A, so you put an A in the middle, and basically you try and find all of the things that could fit that start with a D and then with a C. Just a pair of heteromorphism, one for each of the functors F and G, with the proviso that the output type of one is compatible with the input type of the other. So the A is kind of the type that fits in the middle. As part of Go is pretty weak in the sense that no composition happens beyond the two objects being stored with each other. Right, so I think that's, yeah, that means that kind of rel is weaker than cat in some sense, I think, the way to say that. And that's the basis of what I'm going to talk about. The compose type is just a placeholder for pairs of heteromorphism with actual multiplication. It's being deferred until later. Okay. Similar to the situation with the free monoid, otherwise known as a list. Can multiply two lists together. Right, so it means we, interesting. Yeah, the free monoid keeps all of the elements and doesn't squash them until the end. So it's like the role to squash or to append or to monoidly multiply can be decided later. And you still have all you need with the free monoid to apply it later, which is interpretation or evaluation. So here we're saying, yeah, multiplication is different until later. So free arrow will say how the arrow, what the evaluation of the arrow composition means, and so then we'll decide how to interpret things. And so that's great because it means that indeed if these things are graph-like, especially if we can use them in arrows, then we do build our graph and then we interpret it by defining what multiplication means. The elements themselves are untouched in any way, such as the idea of using a perfunctor composition in the same way that append is used to pair elements and lists. That's not append, that's list concatenation or list construction. So instead, so in a free monoid, we'd keep all elements or generators, I think, or of the monoid, and put the list concatenation between them instead of multiplication, and then sort of interpret concatenation, list concatenation, or list cons as multiplication later. And here we'll do perfunctor composition in the middle. And so I suppose here we mean the sequential composition. I think. And then that would, and then we decide how we interpret sequential composition. I'm probably not going to end up using this. Am I going to use 6P's stuff, 10 people need stuff, because 10 people needs the man. Here's the code. All right. Okay, I think it's time to actually create a dedicated file for this. freearrows.hs. And yeah, we'll need to take that stuff and remove the literate bit. And we need to import perfunctors 562. And we'll need to what will just work? Or do I need to cabal something? Cabal build. It's going to pull functor package. Or not. Ah, yeah, it just makes it visible. And so I probably need to just, okay, it's all good. Just not use now. Okay, fine. Okay, so you define free A. Well, you define free A in the same way that Stuart Fisher defined. No. Wow, it's an intermediary thing. It's right in between those two things. It does have a pure constructor, but then the rest is defined in this kind of CSP way, CPS way. Wow. Okay, mind is already blown. Right, so that's in Fixar. So that's just a constructor, this thing. Oh, wow, it's amazing. We're going to have nice syntax too. Okay, first look at the second line of definition of free A. It says that free A P A B might be a pair consisting of a head heteromorphism. Oh wow, that totally looks like a list of sorts. No, not really. So that would be the nil, and that would be the cons. But the cons, oh yeah, the cons does take a PAX, and it appends it to a free A, so it is like a linked list. Amazing. That might mean ideally that we get like some inductive superpowers to traverse and do things with the graph. That would be pretty incredible. So a head heteromorphism whose output matches the input of another free A. So no, I think this is the pair. Like that's the head heteromorphism, and the output matches the input of another free A. That's what's it there. The pair is that, and then there's the pure P case, which is acting like the empty list. Okay, yeah, so that's nil, and that's cons. So amazing. Okay, I'm going to put it there. That's nil, and that's cons A list A. A, aka A list A. And so here we just have a constructor that will keep track of our perfunctors being appended, but it won't do the composition as far as I can tell, except that it has this for all. So it's something which basically starts wrapping and nesting rank. So it becomes like a rank n type in n being the size of the linked list. That's crazy. Because we'll nest an x each time. What? Crazy. Okay. The reason we use this is that for our composition, function arrow acts a lot like the identity. In particular, composition of arrow and PAB is isomorphic to PAB. I suppose he means compose, right? Compose of F and the P such that the F then becomes AB. So this is DC is okay, this is confusing. Let's write it down. Compose PAB. Compose blah PAB. And then let's write down a definition of compose that actually makes more sense by putting a and a B and then put an X here. Easier to read for me. And then therefore this is actually for X, compose A to B, no, A to X and P X B. And that just means you precompose X with A, and so that's PAB. That I think is the thought. Makes sense. Modulo order user blah blah. This is because an element of this type is a pair consisting of a function A to X and an heteromorphism PXB. For some type X, we don't get to see. Yeah, we can't project back out either of these items with any information about the type of X escaping. So the only thing we can possibly do is to use the LMAP to apply the function to the given element of PAB. Yeah, so yeah, that good old thing of, well, you have a function of A to X. The only thing you can do is precompose it, and so that you get the PAB. Okay. Here's the special case of pure P we'll use later. Okay. And yeah, let's make sure we say this is where this comes from, and then we'll call this module free arrow where, and we'll say that this is this. And okay, so nil is kind of yeah, ID. Sounds fine to me. Like we lift identity, okay. And that gives you what? A free APAA. Okay. And the identity profunctor. What that's going to be useful, I think, for the definition of a category. If I am I right? Profunctor, strong category, pure IDP. Yeah, so that's nil. So I'm right. So an element of free A is a sequence of heteromorphisms. Yeah. If heteromorphisms are thought of as operation of some sort, then an element of free A is a sequence of operations waiting to be composed together into a program that does something based on how you choose what you choose composition to mean. And that's just like the situation with free monads. Yes, once we build a free monad structure, we apply an interpreter to evaluate it. Yes, allows us to separate the pure structure representing what we want to do from the code that actually does it totally. The first thing to note is our new type is also a profunctor. This guy, right? Yes, sure. I mean, obviously, obviously, but I wouldn't be able to write the instance. But should I try to write the instance? Like that, maybe that's a good exercise. Okay. Yeah, don't show me the instances. Okay, where am I? Okay. Yeah, I think that's a pretty good exercise. Profunctor free AP if what? So we have what is that LMAP and RMAP? Ooh. Oh, that's interesting. But I don't think that's what we want, is it? Let's look at the instance. No profunctor instance here. No. Okay. Package profunctor. Profunctor. Yeah. Right. So we can either supply dimap or LMAP and RMAP. Okay. And so I suppose these guys like to propose a map and RMAP. And so let's write the type of that, A to B and a PAB gives you a PABC, is that right? Yeah, gives you a PAC. And then our map, I suppose you can write it the other way around. BC and PAB gives you a PAC again. Thanks. And so it's an F and a profunctor, but in our case, a profunctor is a free A. Well, we can pattern match either on pure P and an F for a G, and then we can also pattern match on how are we going to pattern match on that stuff? I suppose it's a G together with some P. That's inside the list, right? And then we're going to need to recurse. Doing something at some point like lmap fp, I think. And probably we just do this here, and then we kind of like do something like fg, I would think. And then here we do also something like fg, no? Okay, that would be my first start. It's GF, and then the lmap fg h, it becomes lmap fg. Interesting. Yeah, because that's a profunctor. It's not just an F. So we have to lmap to it. But curiously, it doesn't look like we're recursing down into. It looks like we're recursing down on the head instead of the tail. That's very strange. No, actually, we don't. Recursing doesn't mean anything here. We're not recursing. We're just precomposing. So we have an F. We're precomposing with our thing. So we just add it at the top. We pattern match on the G. We lmap the G, and then we leave the tail as it is. All good. And we'll need like instant signatures or whatever, right? Did the wrong shortcut again. And there we go. And what's up? Infinite type. Fine. Well, we won't use instant signatures. And we don't have brackets. We don't have brackets. Excellent. And what's up with that? Oh. Yeah. I see. Yes. Okay. I see. And this needs to be in parentheses visibly. No, it says you don't have brackets. Okay. lmap fg h. Oh yeah, profunctor B or P. Yeah. Okay. Profunctor P. And we're good. We type check. Okay. We also get a strong profunctor. Yeah. So therefore we get an arrow. this is apparently. And we can now concatenate, and then we get a category. Yeah. So I think this means for choice of what composition means. No, actually, we don't need to choose what composition means still at this point. We're just saying that we have some form of what preservation of like naturality in colon dash and composition, maybe. Note that it's slightly different to what you might have expected compared to ++, because we tend to write composition of functions backward. Yeah. Additionally, there is another definition of free A we could have used that's analogous to using snock list instead of const list. Very cool. Okay, I'm going to make a note of that. This could be okay. There's another representation based on snock lists. There's also a representation based on snock lists. Okay. And now we have an arrow. Later proves that the arrow laws are based as an exercise. So thank you for confirming that this is actually an arrow. Awesome. And now what? The important thing about free things that we can apply interpreters to them. Yes, foldr. Wonderful. For list we have foldr, and here we have fold. Oh, that's for control monad. Yes. And then in this case, it's fold free A. Oh, thank you for showing this amazing regularity here, because I think that this is a val and it's just better called fold free. It's kind of nicer, right? Let's check that this is a val. Text pure to RF. So this is any arrow ABC. And so pure P to RG. Is that yeah, pure P to RG. Yeah, exactly. And then G composed with blah, which is the sequential composition, is sec f1 of B to go f2, go f1. So that's the recursion. Yeah, fold free. So the recursion, but only in one branch here. How does this associate? For free f of GH, you end up. Yeah, no, yeah, right. So you recurse on the left, like we did. No, way up there we weren't recursing, but now we're recursing. So here we were precomposing the f onto the g, which is a perfunctor. Here we'll fall freeing onto the head of that construction, and so. Oh, right. No, we're not. Right. So there's a reversal. So that's where the head is, and that's where the tail is, and we're recursing in the tail, except that we keep composing, precomposing. Okay, amazing. I get it. Cool. And then what? Looks a lot like an ordinary fold, but uses the arrow composition law to combine the interpretation of the head with the interpretation of the tail. Electronic components. Ta-da! Let me revisit the example from my previous article. I'm going to remove things I don't need, so my definition of circuit is less general here. Awesome. Free arrows are going to allow us to define individual components for a circuit, but differ exactly how these components are interpreted until later. Oh my god, this is pipelines. This is what we want. It's amazing. I use 4 components this time. A register we can read from, one we can write from, and a register incrementer. Okay, so this is, I suppose, yeah, you're going to define free arrows. Well, let's look at it. Before that, let's revisit Gabriel's article that gives us some clues about how components should be built. In particular, look at definition of teletype F. Okay, so good old free monad there. Okay, so that's the punchline here. Let's see how we're going to use that. So, oh, that's so amazing because I like these kind of constructions. And so, okay, let's read the whole thing. We use getLine to read a string. And yet the type of getLine K could be teletype FA for any A. K being this kind of continuation. I see. I think he's saying that there could be a kind of a fall something in there, which is analogous to the fall we have in our construction here. The reason is that free monads work with continuation. Instead of getLine returning a string to us, it's a holder from function that say that we'd like to do what we'd like to do with the string once we have it. That means we can leave open the question of where the string comes from. The function fault free can be used to provide the actual string getter. Yeah. Free arrows are like two-sided free monads. We don't just provide, oh, that's amazing. We don't just provide a continuation saying that we'd like to do what we'd like to do to our output. We also get to say how we prepare our data for input, the pre-compose and post-compose. There's also some burden put on us. Free arrows need strong perfunctors. Strong perfunctors need to be able to convey extra data alongside the data we care about. That's what first prime is all about. This means that even though load is functionally similar to getLine, okay, let's see the symmetry. GetLine string 2x. We pass it an extra a because we need to be able to modify the input. Is that right? We can simply ignore this input. We don't have load into b. Instead, we have load pair of a int and b. So load. So similarly to getLine. So getLine, if I use getLine in a program, I intend to say that something will be gotten from the driver, the environment, and then I can return that value. I can use the monadic, the arrow notation in do, not the arrow notation, like the reverse pointing arrow in the do notation to say what I'll do once I receive that value, which is getting by the environment. So the load is going to give me an int, which I don't know what it is because it's the environment that's going to give it to me. And then I also get to be in a graph, so I can do something with the input that now depends on what I loaded. Okay. And then incrementing will. That's interesting. So incrementing doesn't even show the int, because I suppose it's doing something in the environment, but what, it's not modifying A or B? I don't know. The component only knows about data passing through of type A and B. It doesn't know anything about how the data in the registers is stored. Right, that's the part that will be deferred to later, yes. So we just have the API to receive something from an interpreter that will be effectful, but this is not tied to any implementation of the register. We intend for inc to increment a register, but as it doesn't know anything about registers, nothing in the type of inc refers to that. It took a bit of experimentation for me to figure this out. Maybe other ways of doing things. Often with code guidance by category theory, you can just follow your nose that there's only one way that works and type checks. Here I found a certain amount of flexibility in how much you store in the component and how much is deferred to the interpreter. Very interesting. yeah, that seems so really, really interesting. There's basically a choice of opaque interpreter or not. Whether ink is a kind of a command in some sense, like it can't modify state, like the graph, the computational graph, I suppose, that's implied by the perfunctor structure. And why do we have arrows here? Could this be kind of PAB? And then could we also make this monadic? Okay, I'll write those questions. Do we need arrows here? Function arrows here, or could we have like ink PAB? Also, or could we have ink a MB? I don't think so. That's the part, I suppose, also where we maybe have flexibility in the sense of whether we want to allow maybe our users to somehow specify something effectful, or whether it's only the interpreter that's enabled to do anything effectful, and all of the effects are in the interpreter. And all of this has a lot of parallel with the design choices of the stuff I was showing actually in my experiments, right? All of this in play, all of this stuff around whether we have the AF in the interpreter, and whether that leaks into the rec and rest, which now starts to look a lot like perfunctorial precomposition and postcomposition, to be honest. Like request is a perfunctor, I'm pretty sure here. Oh boy. Okay, it would make sense that this sort of connects, but let's continue here. I could implement the strong perfunctor instances using various combinators. But I think it might be easiest to understand when written explicitly with lambdas. So you can't derive your component, your perfunctor instance, but you're giving me implementations there, which is cool. Do we have to? No, I think with free monads we can derive this thing. So here we're saying maybe we can't. Right, and then our map. Okay, not very interesting. And the question is, yeah, we'll have to do this manually, which is not the best, but it looks very automatic. Okay, it's fine. And then we have strong. Okay, strong. So that's very interesting. And now we can implement individual components. So that's the same as defining kind of like these monadic values that can then be used with do notation. And now we're going to be able to use these with arrow notation, and that's amazing. Okay, so that's an adder. We have a load that's just basically lifts load. Why not second? Yeah, okay. Can ignore that and store and inc. And then it can be tied into with our notation. Amazing, 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 amazing. What's the type of this? And return. Proc. We have arrows. How do you do type holds in Haskell? Type hold Haskell. What am I doing? Okay, yeah, no, but that's not a type level hold. That's a term level hold. Can you, okay, this. Okay, free a component. Blah blah. And we will have a main. Oh, so at this point, test object is just a list of operation. Right. So that's just a, and we piggyback on the Haskell arrow rotation to define a graph structure that's doing what? It's incrementing the thing. We don't know what that means. It loads it, put the results in A, then loads again, puts the results in B. So that should be the same. Then adds it, and then stores it. And so depending on how many times we use, well, no, test doesn't have an input in itself. But I suppose if it's a global counter, then if we use it several times, then it could be that it's actually, well, we don't have effects here. But I suppose we could have effects in our interpreter. So this is all good. And so there, what do you do? That you're providing semantics. The first uses a state arrow type similar to the previous article. Okay, so that's the implementation using this kind of a state, the equivalent of a state monad. So that just threads state throughout. Okay, and so that's, you call this circuit where this was component. So I suppose that components are kind of abstract, and then circuit is the interpretation we're going to eval from the free A component into circuits, right? Exec, yeah, takes component A, B, and evals into circuits. So we still need to kind of impedance match by giving all of the instances we need to circuit as well. So that's where it's kind of like natural transformation-y, like these evals. It makes me think of like the host thing in like co-free interpreters. And then we exec. And so exec is our interpreter that takes a load of any G and says, well, we're in the state arrow. So you build a state arrow that goes from S, and then load is just going to return S. Store is going to just take the A and put that in the S. We're going to apply G to the Okay, hold on. This is actually doing nothing. I think store just doesn't do anything. Am I right there? Provide a meaning. Yeah, and then inc though, yeah, does this +1, yeah. But store just takes the A and returns a GA. So that's a bit strange, isn't it? Shouldn't we be returning a tuple? Is this G going to build a tuple? Ah, yeah, store does return a tuple. I see. Yeah, that's a strange interaction there. G has returned a B int. So when you pass it the A, it returns the B int. And so we have what we want, the new state. It makes total sense. Holy moly. What about pairs in this setting? Is there a co-free arrow that we can build interpreters from? I mean, basically, yes, there surely is. That's amazing. There is most probably a co-free that we can build interpreters from. And so that would define what, like pairing between perfunctors? I suppose so, right? That be a pairing between perfunctors. And then this is the state perfunctor, a state arrow, and it would have a, and its pairing would be the store arrow. And so that means this is the store arrow, but, or the co-store, or the, yeah, the co-state, is it a co-arrow? I think a co-arrow is an arrow, whereas a co-monad is not a monad. I think that's the case. A co-arrow is an arrow. No? Whereas a comonad is not a monad. So there's an asymmetry in monads and comonads that allow, I suppose, this to happen, but then with the freeness, it could be that there is a co-free co-arrow such that if you define an interpreter that's going to look like the co-free comonadic interpreter in the comonadic UI thing, you still have an arrow, but it'll be the one that pairs with your free arrow, and that can therefore be used as a building block for presumably composing then the interpreters if you have several whatever layers of free arrows. So how does it work? Because in a free monad, in the free monad co-free comonad world, you compose with products and sums, basically, right? or convolution, deconvolution. Convolution. In the free arrow, co-free arrow. I get the feeling that we'll still have exactly products and sums and deconvolution. And then maybe there'll be something else. Here's a completely different interpreter that's going to make you do the work of making the state used by the register. So what to do, we use class IO arrow to do the IO work. Oh, amazing. Wow, this is what I've been looking for. Me like banging my head with this idea of where to put the F. Okay, well, okay, fine. It's the same thing. It's just so much more elegant, but it's the same thing. It's or depending whether you put the F here or there. But yeah, it is the same thing. Classly IOIB is actually A2 IO of B. So it's just like a pretty way to write it. Right, so it's, but the fact that it's then allows you to write this interpreter in IO, that's so good. That's exactly what we want, like a pure version. It's actually, that's not even a, yeah, that is a pure version, but yeah, I suppose it means that we just run circuit, and this really should be store or state, and then we run state A at the edge and just grab the final S, right, and run it with an initial S, and we're done. That's amazing. Okay, let's rename this. I think this is state A, and therefore we just call everything state A, including run state A here. And sure, it's not best, but it's what it is. Okay. You called it something there. State arrow, yeah. So that's right. So here, yeah, we were interpreting into the state arrow. That's not exactly the same as so it means that there's a kind of a run that takes component AB and the co-component AB and interprets it into state A, int AB. Such that the sum pair A between component and co-component And co-component would probably look like a product. Exactly. It would probably be something like load. And store an ink. And it might even be that it's actually the same type signature. I'm definitely not sure of that. Yeah, no, probably not, right? It probably need to be well, we need to have a little bit of that shape, right? A2S. Maybe it would actually be reversed. That's kind of the most likely thing I can think of right now. It's a bit weird that ink would take an AB. Feels a bit like you want it to be into it. You know what? I think this gives a theoretical grounding to choose one of the interpretations in the flexibility. I don't know which one. Could mean that you surface the int in here, surface it also there. This doesn't make sense as an into, or does it make sense as an into int? It kind of does. Huh. It totally does as an into int. Wow. Okay. I've never seen this before. I've never heard of it. Free arrows and co-free arrows pairing. Co-free monad, arrow free, no pairing. That's in Kotlin. Extensible free arrows. Extensible free arrows. In Haskell.
Then you do nothing else. And the same way we can. So let's go through the definition. Another effect for storing things, whatever that
in
is.
Haskell.
So one of the downsides is that when you.
Ooh, I want to see that. Totally want to see that. Okay, herding cats. Okay, so fine, co-free arrows. Not a thing. I suspect this is just co-free. A co-free arrow. Okay, so co-free arrows are a thing. Clearly, though, at this point, a little bit beyond my capacity to understand. But it could be that there's a follow-up blog post here in terms of, I'm gonna write this in my log because I think I have a list of things that might be blog posts in my overall log. Unscheduled blog post about pairing free arrows with co-free arrows. CF streamline src free arrows.hs. Where it is for now. So definitely not a common thing, huh? Click on 3 arrows. Okay, let's punchline, and I'm definitely also losing steam here. So let's try and see what we get. But the next time we get to use these and have fun with them. That's going to be so awesome. Okay, there's more. Labeled. Simply going to some values associated with components. That sounds like the FR, like interpreting into a monoid thing. Monoid M. Labeled some. All right. Oh, right. This is so simple. Look at this. Interpreter for a monoid out into a monoid. Damn, that's really pretty. So that means that arrows, I suppose, like applicative, are can be introspected, or is that introspection? I think it might count as introspection, right? This could be a different AB, but I'm fine with that. And right, because AB here are actually ghost parameters. Ghost types. Now that we can't assign non-trivial values to pure operation. Oh. Yeah, what were we doing with those? We did have this pure constructor, but it didn't show up. It showed up in add for some reason. Okay, as an operation that, well, I suppose doesn't depend on sort of the, I don't know how to call them, like the co-free, yeah, the free arrow. It doesn't really depend on the free arrow. It's just lifting plus. But then we didn't have to introspect and treat the pure case, because I suppose that the pure case is only used to lift things, to lift pure functions into free arrows. Okay, and here a pure function what does it say? It says like we're not counting pure functions. That's what it means. Some valuation to various component because in dollar time to execute if instruction depending on the simple execution trace. That we can't assign non-trivial values to pure operations. Okay, so can we assign trivial values to pure operations? Yeah, I suppose we can assign just unit or, but we can't distinguish, we can't introspect pure operation is what's going on. And yeah, so how do we execute this? Can we just cabal, can we just cabal run like src 3 arrows? Is that possible? No. Can we just, so shall we just gc? Sounds like it. Did you build an executable from that? I think, yeah, well, we wanted to run GC. Holy moly, it just works. I'm so impressed. And this is the okay, so this is really amazing. And next things that we can try here, I'm so excited to try this thing. So we're trying 3 arrows and it's just working super well. Build a graph, interpret into, do we even want to interpret into a visualization? We just want to interpret into a pipeline. That's just what we want. So we need then to think about mutation of the free structure. And that starts to become a little bit more tricky, right? That seems like maybe then we need something like parametric higher order 3 arrows. Is there such a thing? Raising the stakes. Because right now we'll be committed to a graph like this, right? And if we want to change it, we need to recompile the code. So if we want this to be, if we want to raise this up, then we need an interpreter of arrow code, right? Unfortunately we lose the elegance of using arrow notation in Haskell. But I suppose what we could also do is just use JCI as an interpreter or something. Like a bit like what Tyrion has been doing with the essence of data flow programming. Then we don't have, then we can at least for a while piggyback on the Haskell interpreter and not have to create a language and deal with all of the overhead of parsing and all of that stuff. So that could keep us going for a while. So what would it look like then? It would look like that we define our pipelines in some Haskell file. It will look a bit like this. It will put in the GST elements. And then what? And then, wow, then we'll need to do the similar thing that Tyrion does by maintaining state, possibly between interpretations. And then maybe even further, being able to hook into like diffing of the of the free arrow structure? I mean, free arrows are just a data structure. So maybe there's a diff, maybe we can write a diff function. Oof. Yeah, sounds pretty cool. For when we take the leap towards defining our own language on top of Haskell would probably be the way it's done first. But that means we'll need all of the kind of incremental parsing machinery and all of that stuff. Which at some point we want to build. That's kind of the direction of like more the, yeah, that's a whole other thing that is not part of our project so far, but that's been in the back of my mind. Very cool. So that feels like tons of progress. Do we have a solution for this? Yeah, I think we have a solution for these type changing things too, because it works in like an heterogeneous data structure, because those are basically sort of type indexed kind of structures, you could call them. Because they have an A and a B, and so you can do what you need to do. I wonder what it would look like to try and define like a cap or a terminator, like the initial source and a final sink. And yeah, so looking forward to play with this more. Thank you so much for watching, and I will see you in the next stream, which should be on Tuesday. Take care and bye-bye.